Vacuum infusion in the composites industry. Composite materials use materials in what they are best at. Reinforcing fibers for stiffness and strength while using a polymer matrix for shape and durability. Combining in an intelligent way the wide range of fiber and matrix combinations available. Composites offer as no other material the possibility to tailor the material to the required properties, making effective use of materials, allowing significant weight reductions over other materials. A comparison of a simple plate-loaded inflexure shows that while maintaining equal stiffness, a weight-saving factor of 5 can be attained by simply using a composite sandwich solution, compared to a conventional steel solution. Even over aluminium, a weight saving of 2.5 can be achieved. A large part of composites' advantageous properties stems from the reinforcing fiber used. A large range of fibers is available, but the three dominating ones are glass, carbon, and aramid. The white glass fibers offer a good cost-performance ratio, and are therefore the most common choice in composite applications. The black carbon fiber is typically used where weight savings are critical, and where its performance justifies its price. The yellow aramid fiber is especially used when toughness is required, like, for instance, in impact or ballistic applications. The choice of polymer matrix, apart from influencing mechanical properties, determines additional properties like chemical resistance and service temperature of the final product. It also largely determines the ease of processing of the final composite product. Polymers can be roughly divided in two groups: thermosets and thermoplastics. Thermosets typically offer easier processing, while thermoplastics require more complex processing. Thermoplastics, however, can be easily recycled and are typically tougher. The total suite of requirements determines the best choice for the final product. Current composite processing techniques make predominantly use of thermoset polymers. Processes like spray-up or hand lay-up are widely spread due to their processing ease and low investment requirements, allowing for small and variable series. However, they offer limited properties and product quality. On the other end of the spectrum, autoclave-based processes offer outstanding properties, but are slow and expensive, requiring large investments in equipment and use of costly materials. The resin transfer molding process, or RTM, injects a resin into a stiff mold that contains dry reinforcement. Though offering increased product quality, still mold investments are high and part size is limited. Vacuum infusion offers an alternative to existing processes by combining low investments in materials and equipment with the high quality of autoclave processes, while having no inherent product size limit. In this process, fibers are placed in a mold covered with a vacuum-tight film, and vacuum is applied to impregnate the fibers with resin. Due to the use of only one mold half that can be made out of polymer or foam instead of expensive steel or aluminium, and the reduced investment in equipment, the process is very cost-efficient, while at the same time offering a quality that can compete with that of composites made using autoclave techniques. The driving force in this process is vacuum. The dry reinforcing fibers are infiltrated with polymer resin by the use of a pressure difference. When the pressure difference is applied by the use of a simple vacuum pump, the resin will be pulled through the mold, thus impregnating the dry fibers. The process offers high fiber volume fraction, as the dry fiber is compacted by the vacuum, and only interfiber space is filled with resin, effectively reducing excess resin weight. Product thickness is consistent as it is determined by the thickness of the compacted layers of dry reinforcement. Thus, the process offers consistently high product quality. The process allows for obtaining large structural components with a high-quality surface finish like this boat hull. Before molding, typically a protective outer layer, called gel coat, is sprayed or painted directly onto the mold. The gel coat protects the underlying composite and gives it a good appearance. For more demanding applications, an extra barrier coating can be applied for additional protection. The composite product can be directly made on top of these layers. That will form an integral part of the final product. In order to maximize the potential of vacuum infusion, some basic rules have to be kept in mind that determine the process time. Darcy's law describes well the time needed to fill a product and shows its dependency on various process parameters. As can be seen, especially the flow length is critical in reducing the fill time. The figures give an example of how the fill time for the same product can vary, depending on the number and position of the resin feeding channels. The example shows how optimization of simple parameters can lead to largely reduced process times, without affecting quality, thus offering important cost savings. The practical application of these rules to the infusion of the windmill blade shows how infusion time can be reduced from 55 to 20 minutes by changing from a root-to-tip infusion strategy to an infusion that is starting from the center axis of the blade, thus dramatically reducing flow length and fill time. For more complicated structures, modern, easy-to-use software tools are assisting in planning the right strategy for the infusion process. They optimize processing time and minimize the risk of, for instance, air enclosures. In this way, critical areas can be detected, fill times estimated, and positions of feeding channels modified at an early stage in the design process, thus avoiding expensive trial and error processes and investments in wrong molds, tooling and materials. Such simulation tools were, for instance, used to define the infusion strategy for this boat hull, of which the infusion model is shown on the right. The pink line shows the infusion channel where the resin enters the mold. The blue dots represent the venting ports where vacuum is applied, and thus where the resin exits the mold. The colored picture at the bottom shows the filling progress during the infusion process. The model predicts the flow progress, which can subsequently be optimized and used in the final production. The left picture clearly shows the layout of the runner channels as determined by the simulation software. The center picture shows the entrance of the resin through the central runner, and its spreading to the smaller side channels. In this way, resin is evenly distributed over the entire structure, minimizing flow lengths and thus fill time. At the same time, the risk of enclosed air is minimized. The picture on the right shows the final stage of the infusion process, as the resin is reaching the venting ports. Due to its inherent advantages of low weight, low investments, infinite size, and structural properties, vacuum infusion is seeing a significant growth in the aeronautics, marine, and coach building industry, as well as for wind turbine blades and for civil structures such as footbridges. Our group aims to transfer the vacuum infusion technology to your industry, making it work for your product. We thereby offer services all the way from product concept, through engineering and prototyping, into series production. Don't hesitate to talk with us about your product. We would be pleased to work with you.